Hello, and welcome to Cytoflow. In this screencast, I'm going to demonstrate some of Cytoflow's basic functionality. More advanced features will be covered in additional screencasts. I'm going to be using data from the basic example zip file on the Cytoflow website. Feel free to download it and follow along. Cytoflow takes a different approach to analyzing flow cytometry data. It assumes that you have FCS files that represent different experimental treatments and that you want to determine how the different treatments affect the distributions of fluorescent measurements taken by your instrument. To begin an experiment, we have to define this mapping between FCS files and experimental variables. We do so by clicking Edit Samples. First, we'll add some FCS files. Click Add Tubes, and then select the files you want to add. Note that you can select multiple files by selecting the first file, holding Shift and selecting the last, or alternately, by selecting the first file and then holding down Control and clicking multiple files sequentially. I'm only going to load 9 files for this example. Next, we define the experimental conditions that changed in each tube. In this experiment, I treated cells with increasing concentrations of an inducer, and I want to analyze the relationship between inducer concentration and GFP expression. So, I create a new experimental condition by clicking the Add Conditions button. Conditions can be categories, numbers, or true-false values. In this case, I'll choose number, and I'll call the new condition inducer. Now, I need to fill in the values of the experimental condition for each tube. Note that as I fill in each value, the row changes from pink to white. A white row indicates that the tube has a valid set of conditions. Each tube must have a unique set of experimental conditions. If you have technical replicates, for example, add a new condition named replicate and number your replicates 1, 2, 3, etc. Once all of the tubes have conditions, click OK. The main Cytoflow interface is divided into 4 panes surrounding a central window. On the right side are options for plotting data. Let's start with a histogram by selecting the histogram icon here at the top. Once the histogram view is selected, the View Properties pane is populated with a set of controls that let you select what is plotted. In this example, let's choose the FITSI channel where we see GFP. Note that as soon as the channel is changed, the display updates. In most instances, changing a parameter will update the display automatically. This plot is not terribly informative because it's on a linear scale. To rescale the plot, change the scale property. I like logical, which is linear around 0, but becomes logarithmic after about 100 or so. And now we can see that there's some structure to this data. It's very important to note that by default, we are viewing the entire data set. That is, this isn't a single tube, but all 6 tubes that we loaded plotted at once. If we want to look at subsets of the data, we have 2 options. First, under the subset property, we can specify a range of inducer concentrations. For example, if I slide the bottom slider all the way up to 5, then the plot I get is only the cells that had an inducer level of 5. The second way to look at subsets of data is to use facets. Cytoflow's visualization takes inspiration from lattice plots, which use subplots to compare different subsets of a data set. Once we've reset the subset control, then we'll go up to the vertical facet, and we'll choose inducer. Now, instead of a single histogram of the entire data set, we've got 6 stacked histograms, each of which represents a single inducer concentration. And we can see that as we increase the inducer, we see an increase in fluorescence signal in the FITSI channel. Now, I know that there are rather a lot of controls for the histogram plot, and that can be confusing for newcomers. You can get help down here in the Help pane by default in the lower left corner of the display. If you're an expert, you can close this pane by clicking the X button. You can make it reappear by selecting it from the View menu. Okay, so now you can plot data with the views on the toolbar on the right side of the screen. The tools on the left side of the screen allow you to manipulate data in various ways. These operations range from basic gates to calibration operations like bleed-through correction to sophisticated statistical models and machine learning methods. We're only going to cover a few basic operations in this screencast. For more, I encourage you to check out other screencasts on this channel. Let's start by drawing a gate that will help us choose events that represent single cells. We'll use the polygon operation, and we're going to gate cells based on their forward and side scatter signals. So I'll set the channel that's displayed on the x-axis to forward scatter, and the channel displayed on the y-axis to side scatter. Again, because this is plotted on a linear scale by default, this plot isn't terribly useful. So let's go ahead and change the scale on both of those axes to log. Now, I'm going to draw a fairly aggressive gate around the main population by clicking sequential vertices of the polygon. When I'm done, I can close the polygon gate by double-clicking. Note the error that is below at the bottom of the polygon operation. To make the software happy, I have to name this gate. Let's call it Morpho, short for morphology. Now let's go back to our histogram view. Under Subset, you can see that in addition to the control for changing inducer level, I also have a control Morpho plus and Morpho minus. If I use the histogram to look at the FITSI channel again, and again, we'll rescale it to logical. Now, if I select Morpho plus, I'm only looking at the events that were inside the Morpho gate. And if I select Morpho minus, I'm now looking at cells that were outside the Morpho gate. So let's create our original histogram by changing the vertical facet to inducer. But let's also set the vertical facet to Morpho. Now instead of 6 plots, I've got 12. On the left are the events that were not in the Morpho gate, and on the right are the events that were. It doesn't look like these populations are terribly different, though of course there are many more events that are inside the Morpho gate than outside. To make comparing populations that were outside versus inside a little easier, I can use the color facet instead of the horizontal facet. Though note that once I set the color facet to Morpho, I have to reset the horizontal facet to none. I can't reuse conditions in facets. So now there does appear to be a little bit of a difference in the cells, in the fluorescence of the cells that were in the Morpho gate versus outside of the Morpho gate. For example, down here at an inducer of 1, you can see that the ones that were outside the Morpho gate might be, on average, have a little bit higher fluorescence. What does this look like from a really quantitative sense, though? The ease that you can answer these kinds of quantitative questions is one of the things that sets Cytoflow apart from other tools for analyzing cytometry data. So let's go back to our operation toolbar, and this time we'll choose the big sigma, which will add a channel statistic. What this operation does is it divides the data into subsets, then applies a summary function to each of those subsets. As with gates, we have to name the new summary statistic, and so this one will go ahead and name GFP after the species that we're measuring. We choose the channel that we want to summarize. In this instance, it's the FITSI channel, and we choose the function that we want to apply to that channel. In this instance, because the population in the FITSI channel is unimodal on a logarithmic scale, we're going to use a geometric mean. Now here is the key part of using the channel statistic operation. We tell the operation how to divide up the data by using this group by parameter. If I select inducer, I'll get 6 geometric means, 1 for each inducer level. If instead I select morpho, I'm going to get 2 geometric means, 1 for all of the events that were inside my morphology gate, and 1 for all of the cells that were outside it. However, if I select both, Cytoflow will compute 12 geometric means, 6 for the inducer levels where the cells that were inside the gate, and 6 for each inducer level for the cells that were outside. It's a little clearer if we go to Views and we choose the table view. First, I select the statistic that I just created, and now let's set rows to the inducer condition and columns to the morpho condition. Now you can see the geometric means for each subset of the data. If I want to export this export this data to a CSV file, I can do so by clicking the export button here. However, I can also plot this data right here in Cytoflow. To do so, let's choose a one-dimensional statistics view. Similar to the table view, I start by choosing the statistic that I want to plot, and then I choose the variable in that statistic that I want to be on the x-axis. There's only one available here, and it's the inducer concentration. When I do that, by default, the other slices of this data set, in this case, the morpho gate, the morpho facet of this statistic, show up in tabs up here on the plot, on the top of the plot. However, I can compare all of them on the same plot by coming over here to hue facet and choosing morpho. I can also change the x and the y axis scales, both of which make more sense on a log scale than on a linear scale. And now it becomes clear that there is actually a little bit of a difference between the geometric mean of the GFP as measured in the FITSI channel between the events that were inside the morpho gate and the ones that were outside the morpho gate. Is that really quantitatively different, though? Let's see how different they are by computing a second summary statistic. In this case, we're going to choose the large sigma again, which adds another channel statistic operation. We can continue to use the GFP name. We'll measure it in the FITSI channel, but this time, instead of choosing geometric mean, we're going to choose a 95% confidence interval around the geometric mean. It is very important to make sure that we choose both inducer and morpho under group by. Now, if we set up another one-dimensional statistics view, there's a second statistic to choose. So we'll choose geometric mean as the statistic we want to plot. Variable remains inducer. Color, the hue facet is morpho. We'll go ahead and rescale both axes to log. But now, if I choose error statistic, I can plot that 95% confidence interval on top of this plot as well. And because those confidence intervals overlap, both when morpho is true and morpho is false, except of course for this one inducer concentration right here, it becomes a little more clear that there's not actually a terribly large or a terribly statistically significant difference in the geometric mean between these two populations. Now, I am not going to claim that this plot is the most beautiful thing in the world. However, as of version 0.9, Cytoflow gives you access to more fine-grained control over the visual parameters of the plot, and you can change those down in this panel labeled plot parameters. One thing we could do is we could make the x-axis limits better. So, for example, let's go ahead and change the lower limit of our x-axis to 0.05. And now we can actually see that entire bar. We can also change things like the line style or the plot marker. However, with an error statistic like this, possibly the most useful thing we can do is, instead of using vertical bars at each plot marker to demonstrate that error statistic, we can turn it into a set of shaded polygons. We can also change the axis titles. Let's go ahead and change the y-axis label to GFP, geometric mean in arbitrary units. Finally, if I want to export this plot, I can do so by coming up here to the Save Plot button. And if I click that, I still have access to my plot parameters. I can also choose the width, the height, and the resolution of the exported figure. And then by clicking the button, I can give it a file name. The supported file formats are displayed here in the drop-down. And then to return to Cytoflow, I click the Return button. Finally, while Cytoflow is sufficiently stable for everyday use, there are still occasional bugs. And if you encounter one, I encourage you to report it to the developers by going up here to the toolbar and choosing Report a Bug. Once you do so, you actually have two options for how you report that bug. First, you can email the developers. If you choose this button, Cytoflow will try to start your email program and open a new email with bug template for you to fill out. It will also include a lot of logging information that will help us pin down the source of the problem. If instead you click Save to File, the logs will be saved to a file, and then Cytoflow will try to open your web browser to the Cytoflow issue tracker. Thank you in advance for telling me where it breaks for you. I hope you found this introduction to Cytoflow useful. There's a ton of power here, but the interface makes it easy to discover and explore. I encourage you to read the help on the operations and views and to check out the additional screencasts for some more advanced examples.